So in this video, we're going to talk about the energetics of chemical reactions. But before we get to the chemical reactions, I want to introduce the concept of potential energy. I think you guys all have sort of heard about this before, learned a little bit about potential energy, and I'm guessing that most of your experience with potential energy is in the form of gravitational potential energy. They might not have labeled it as gravitational, but this is probably what you've had in, say, physical science or middle school science. So, for example, let's say you've got a boulder on top of this cliff. Okay, you've got this cliff that's 100 meters high, and let's say the boulder is 1 kilogram, and you may remember from previous science classes that this boulder is going to have a certain amount of potential energy, and potential in the sense that if you give it a little nudge, then it's going to fall to the ground, and in falling to the ground it converts the potential energy to kinetic energy, and when it hits the ground it's going to make a big boom, probably make a little impact crater, and so that's an illustration of potential energy by virtue of its position above the ground, and how potential energy gets converted to kinetic energy. So that's one form of potential energy. And the thing, one of the keys here, and because this is going to carry over into chemical reactions, is that as the ball transitions from a higher state of potential energy to a lower state of potential energy, it reaches a more stable configuration. So, I think it kind of makes intuitive sense that this boulder is a little more stable now that it's at rest on the ground than it was when it was perched up at the top of the cliff. Okay, so again, the lower the potential energy, the more stable things tend to be. Now, let's move over to a chemical reaction and see how potential energy applies to chemical reactions. All right, so here's our old friend. We've seen this chemical reaction lots of times. This is how we make water by reacting hydrogen gas with oxygen gas. It takes 2 moles of hydrogen with 1 mole of oxygen to form water, and you get 2 moles of water out of the deal. We're assuming that all 3 of the substances here are in the gas phase, and then these are just kind of like little, little models, little pictures of the hydrogen molecules and the oxygen, and then what the waters look like. So you can see how the bonds are rearranged going from reactants to products. Okay, so what we know is that water is at a lower potential energy than the hydrogen and oxygen gas that it's made from. And experimentally we kind of know this, and you guys have seen this. You'll remember we did that crazy demonstration where we reacted hydrogen gas in a bottle rocket. We lit a match, and it sent the bottle rocket across the classroom. And so when you react these two things to form water vapor, it releases a lot of energy. And so that's a hallmark that, just like when you push the boulder off of the cliff, chemically that kind of happens too when you have reactions like this, where you're going from reactants that are relatively unstable to products that are much more stable. Okay, so this is one thing that we can say about this reaction. The product, water, is at a lower potential energy than the reactants. Why? Well, because overall the product molecules, water, they are more stable. They're more stable molecules than the hydrogen and the oxygen together. And just to go a little bit more deeply, one of the reasons that the water is more stable is because the chemical bonds that hold the oxygen and the hydrogen atoms together, these bonds are stronger than the hydrogen bond. I'm sorry, not the hydrogen bonds, but the bonds that hold the hydrogen atoms together. The double bond that connects the 2 oxygen atoms in a molecule of oxygen, it's pretty strong. that's a pretty stable molecule, but the hydrogen is not that stable compared with water. So overall, you get a drop in potential energy, and when you do that, energy is released, as we've seen with the bottle rocket demonstration. The question: how much energy? Well, it's been measured carefully. And it turns out that when 2 moles of hydrogen gas react with 1 mole of oxygen to form water, it releases 483,600 joules. And that can be written a little bit more conveniently by converting the joules to kilojoules. Notice there is a negative sign here, which is an indication that this is an exothermic reaction. Okay, so when these two things react, heat energy is released. And that when heat is given off, that's an exothermic process, and the sign of the heat is negative. Now, so that's just kind of the broad brush to kind of introduce you to the energetics of reactions. And I just want to take a short little diversion here into what this symbol is. So we've been used to talking about heat by using the symbol Q, but here you can see that we are using the letter delta H, or the symbol delta H, and then the RXN stands for reaction. Okay, what is that? Delta H, this is the symbol that's used in chemistry for the enthalpy of reaction. Okay, and here's the definition. You can read it yourself. And what distinguishes enthalpy from just plain heat, which we symbolize with Q, is it's basically the same, but the distinction is that it refers to processes that are carried out at constant pressure. Okay, so if you do a reaction and you measure the heat that's transferred either into or out of the reaction, if you do it at constant pressure, then we call this an enthalpy. All right, and I know that sounds like that's a funny term, but this is what we use in chemistry, and so I want to get you used to it. And again, it's pronounced enthalpy. Now, there are several different little symbols that are used in addition to the delta H. One is you'll see a little. This is a 0 superscript, and this indicates that the measurement was obtained on substances in their standard states. Okay, so let me go back. In this reaction, hydrogen gas at atmospheric pressure and like normal room temperature is found as a gas. Same thing with oxygen, and so these would be the standard states of hydrogen and oxygen. Okay, so that's what's meant by the 0. Then furthermore, you can see the symbol with a subscript F. The subscript F indicates that this is a heat of formation. And I'll show you a table of those in just a moment. Sometimes you'll see it with a subscript C, and that indicates that it is a heat of combustion. Okay, so whatever the compound is, it's reacting with oxygen in a combustion reaction. And then finally, you'll see something a little bit more generic. You may see just RXN, like you saw in the last slide. And the RXN subscript just means that it's an enthalpy for the reaction as it's written. Okay, now just so that you I'm not crazy, I'm not talking about things that are completely far out. Here's a table that is used in chemistry quite a bit. It's a table of enthalpies of combustion, and you can see, like for hydrogen, it's telling you that when you react 1 mole of hydrogen with oxygen, you will release 285 kilojoules of energy, and so on. You can go down and see what's going on with propane, and you can see that propane, when you burn it, releases a lot of energy, and that's partly what makes it a really good fuel for outdoor grills. Here's a table of enthalpies of formation. Okay, and you can see there's a wide variety of those. Okay, so that's just to give you a flavor of where you might see these. Okay, so now usually we've written the reaction where we have the hydrogen and the oxygen on the left. However, you can run this reaction the other way. You can, if you put enough energy in, you can break the bonds in the water molecules and reform the constituent elements, hydrogen and oxygen. So you can run this reaction in reverse. Now, it doesn't matter which way you run the reaction. The water is still the most stable compared to the hydrogen and oxygen. And that energy difference, you may be wondering, it's the very same thing. It's 483.6 kilojoules, but this time, because we're going uphill in potential energy, then it means that we would have to supply energy to make the reaction go. Okay, it'd be kind of like pushing, rolling the boulder back up the cliff. It takes energy. There's an energy input, and that's what the positive sign is telling us. Okay, so what that means is that the way the reaction is written here, the product molecules now are less stable. And so energy is absorbed by this reaction, and therefore we would categorize this as an endothermic reaction. Okay, so that is it for this slide. This was just to kind of give you an overview of the energetics of reactions, introduce a few concepts, and just kind of give you an overview.